So, Rosemary, in the United States, it's sort of golf season. So every weekend you turn on and there's some crazy golf tournament. I'm not a golfer. I think Joel is, actually.
Are you serious? They show golf on TV?
I know, it's sad, isn't it?
We show cricket on TV here, and that's probably close.
But in Australia, they're having problems because I guess there's a lot of wildlife on the golf courses, like kangaroos. And I saw a picture this week of like 30 kangaroos hopping around this golf course where this caddy is. I'm thinking, my gosh, is it just the wilderness in Australia or what? Like, you can't even golf in peace in Australia. You can't swim in peace. You can't golf in peace.
Kangaroos love golf courses because, they like open grasslands. Traditionally, there wasn't that much open grassland in Australia. And so they've really thrived where we've come and made lawns. They absolutely love that. They don't drink water. They just eat it off the dew on the grass, and then they hang around eating grass. And yeah, they're like, great, these people have come here and put in all these lawns for us, and they keep them nicely mown, soft on our feet. If you're a kangaroo, isn't that where you'd want to hang out?
I totally would, yeah. I would stay away from the other dangerous areas of Australia, like pretty much everywhere else.
Well, a kangaroo can mess you up.
It's probably one of the most TikTok things that I've ever seen are kangaroos fighting people, weirdly enough. I don't know what it is in America. We think that we can manhandle a kangaroo, but you're out of your mind. Those things are powerful. You're crazy. And then don't they have sharp hooks or whatever on their feet? Claws? Oh, they call claws?
I don't know. I wouldn't worry about their claws. I guess they got claws on their hands, but their arms are not that strong. No, you got to worry about getting kicked. They sit on their tail and then they kick you with both legs at once.
Can't wait to book a trip to Australia.
Yeah, well, if you do, just don't pick a fight with a kangaroo.
All right, Rosemary, hold on tight. This one's going to be a good one. Xenecore is a company that develops materials and processes for composite parts, and they have a new technology, or one of the company technologies, on using thermoplastic microspheres. And I don't know if you've seen microspheres in use, Rosemary, but it's sort of a thing you add in to make really cool composites. Well, they're using it in a structural lightweight foam. And as part of that, they've found an application which is drag-based wind turbines, or basically fan-shaped wind turbine blade design. So it's more based on like the old style Holland, Denmark wind turbine, not even wind turbine. Like, yeah, it's just the wind hits it and it spins, sort of thing. So the design idea is to make these fan turbine blades from a one-piece monocoque construction with reinforced carbon fiber and epoxy in this foam. So it's sort of a slick way of making these blades. Now, they're throwing out some numbers about the efficiency of these things, and their contention is in low wind conditions, these drag-based designs are more efficient than the typical aerodynamic blade design we see all over the world. And when I read that, I thought, oh, come on. That can't. Really? So here you go, Rosemary. It's all yours.
Yeah. So I guess the first thing is to say that, drag-based is inherently less efficient than lift-based, and it can't be otherwise. And I'm trying to think of a good way to explain that, but an aeroplane flies, right, because of the magic of lift. The lift force is really big. And if you compare that to, the kind of force when you're standing there and you're going to get blown over by the wind, it's just a lot bigger. So if you stick your arm out of the car window and you've got your hand flat, to act like a sail against the wind, then that's going to, push a certain amount. And then if you can kind of like tilt it so it acts like a wind, then maybe you've felt that you can actually get quite a high force when you angle it right and you get a lift force. That's, it's surprising how hard the lift force is. When you look at the equations, you're never going to get the same power from a drag-based system than a lift-based one. I do think that when you look at this, their design, it looks like the kind of thing that I know that people who don't understand how wind turbines work are going to think, oh, that's much better. It's going to be much more efficient because they've got these 4 really big flat blades. And when you look at it, you nearly can't see through it, right? The blades are nearly covering the entire area of the disc. And one thing that I get told a lot on my, the comments on my YouTube channel is they should put more blades because all the air is just rushing through. There's so much space in between those blades. Why don't they put more blades on and capture more of the wind? But because the blade is turning, if you have designed your lift-based, 3-bladed or however many blades you want to put on there, if you've designed it properly, every air molecule that goes through that disc is going to interact with a blade and have its energy, some of its energy taken out. So it's because the rotor is turning at the same time as the wind's going through. So an air molecule is moving, and by the time the next one gets there, the blade has gone a bit further.
The blades are moving faster than the air molecules, velocity, speed-wise, right?
Yes, that's true. And so, they all get affected by the rotor, and every air molecule in a well-designed turbine is slower than, when it exits the wind turbine than when it entered it. So that's the first thing. But I can see that it definitely looks, to someone who doesn't understand that thinks that most of the air is just rushing through without having any energy taken out, it looks like this new design is going to be better. But yeah, when you read through what the company is saying about their new wind turbine, I mean, it sounds like a really cool material. I will definitely give them that the material sounds cool. And the article that we're talking about is in Composites World, and that's a materials publication, not a wind energy publication. So that part of it, yeah, cool. But it just doesn't give the impression to me that the whoever designed this wind turbine understands how wind energy works or what the current state of the art is, or not even state of the art. Like anyone can build a backyard wind turbine that would be more efficient than this one if they did it, a lift-based one. But yeah, they're talking about how, back in the day, all wind turbines were drag-based, and the reason why they weren't very efficient was because of materials. So now we've solved the materials problem. But it's just wrong. That's not why the old turbines weren't efficient. And so, yeah, changing to a better material is not going to undo that. They also said, they fall into the same thing that you see a lot of people with new wind energy, people outside the industry who come in with a new way to make wind energy. They often fall into this kind of arrogance, I'll call it, where they're like, oh, well, obviously the whole wind industry, it's full of mindless automatons that just are, copying what everybody else did in this massive group think, and no one is ever thinking originally. And so, the only reason why this is done this way is because it's always been done this way, and I've thought of a different way to do it. And so they say, there aren't analysis methods for anything other than the traditional wind turbine, and that's why you don't ever see anything different. Whereas it's the other way around. The reason why there's a lot of design tools for, the modern type of wind turbine is because that's what works and what everyone wants to make. Anyway, so they've said, they've found an analysis method, and it's ANSYS, which incidentally is like the most common finite element analysis and computational fluid dynamics software available. That's what I used in my PhD research and what many people use in industry. They've done some, I assume that, someone has taken a day or two to learn how to use this very complicated software, because then they've ended up with results that don't make any sense, which is saying that drag-based system is better than a lift-based system. And with CFD, I found when I was doing that using CFD in my PhD research, I was doing load distributions to, figure out which parts of the blade needs to be how strong, basically. And you can get any result that you want if you aren't validating it. So CFD is really good for, doing design iterations, for making small changes and seeing how you expect that would change things. What it's not good for is starting from a brand new concept and saying, what's this going to do? Because you've never made it. You don't have anything to pin it to. So you can just tweak parameters in your simulation until you get whatever result you want practically. I had to go to a lot of trouble to find a reference design where I could model it and have an actual physical test that I could tie that result back to before I could then make any changes in the model, because otherwise it's totally meaningless. You might as well just write down a number that you wish that it would generate, and why even bother doing your analysis if you haven't got something to tie it back to. And it's the same problem when you often see reports of better, more efficient wind turbine designs reported, but it's only done with CFD modeling, and it's total junk. I wish that people who are writing articles would learn that point, that if you haven't made one, you haven't validated your model, then it is totally worthless. It's worse than worthless because it makes people think that they've got something. But the other interesting thing about this, I went onto the site, the fanturbine.com, fan turbine by Xenecore, yeah. I mean, they've got a lot of issues that every new wind turbine design. I often go through and tear apart new designs that are not really new. I mean, this one legitimately does look different to anything I've seen before. So they've got that, but they make a lot of claims that they can't back up because it doesn't exist yet. So price, the annual output, reliability, their startup wind speed. Guess what their startup wind speed is, Alan?
2 meters per second?
No, it's 1 mile per hour, which is less than half a meter per second. So 0.3 watts it's going to be making it at half a meter per second wind speed. So yeah, that's one of the things that you see over and over again for new wind turbine designs, especially small ones, is it works in low wind speeds. And it's like, okay, what are you going to do with 0.3 of a watt? Really, nothing probably. But I also calculated the efficiency based on what they've got a power curve there for it. And I did this while we were talking, so it's possible that I made a mistake, but it seemed like they're calculating 40% efficiency, which is too high for a drag-based system, definitely. But on the other hand, also less than a regular wind turbine, horizontal axis lift-based wind turbine. So the claims don't add up, which obviously they wouldn't. But I don't know. It's disappointing to me to see this. Composites World is that's a respected publication that I trust for news about composite materials, and I'm a bit disappointed to see the ridiculous wind energy stuff in there, but I'm frequently disappointed, so there you go.
Hey Uptime listeners, we know how difficult it is to keep track of the wind industry. That's why we read PES Wind magazine. PES Wind doesn't summarize the news. It digs into the tough issues, and PES Wind is written by the experts, so you can get the in-depth info you need. Check out the wind industry's leading trade publication, PES Wind, at peswind.com.
Well, maybe we ought to keep on the new innovative technology front in the news, and I want to bring this into the discussion because I think this sort of ties in with things I'm seeing generally speaking in the sort of the venture capital innovator hub in wind. The Offshore Wind Innovation Hub has selected 6 startups to participate in their first accelerator program. So the Offshore Wind Innovation Hub is a collaboration between Equinor and BP, the Urban Future League, the NYU Tandon School of Engineering, and the National Offshore Wind R&D Consortium. So it's like all around New York City, right? And it's supported by the New York City Economic Development Corporation. There you go. And they had basically a Shark Tank event, and there was a pool of 49 applicants from all over the world, and they chose 6 of them to move on to the sort of the next phase, which includes mentorship, business development support, and access to offshore wind industry around the New York City area. So there's a lot of smart people down there. It could be really helpful to you. The companies that they chose, let me read them off. Benchmark Labs, which is a turbine-specific weather forecasting piece of software, it sounds like, to improve operational margins. So maybe knowing a little bit about what kind of wind's coming in. Flucto, which uses sensors, GPSs, and camera data for offshore wind farm installations to increase precision. Harima Engineering Solutions, which is creating a software tool to simulate and complete offshore construction processes in an event simulator, kind of Star Trek-y. OCS AS is talking about industrial metaverse simulation for de-risking and cost-cutting offshore wind farm planning. RCAM Technologies, RCAM Technologies, is a low-cost 3D printed, environmentally friendly concrete anchors for floating offshore wind. And then the last one, which is Vinci VR. It's a virtual reality for workforce safety and training. So all these are interesting, and I think they probably could add something to the offshore wind industry. I always just wonder, like, how applicable is it? And are there other companies that are not already doing these things, particularly like on the weather front? There's a lot of companies that are involved in weather at the moment, Vaisala being one of many. Is there anything here that really stands out, like, oh, that's a really cutting-edge technology, we needed that 5 years ago?
I think all of them seem to be solving real problems. So that's at least a start. None of them jumped out at me as being something that nobody else is trying to do currently, or, that doesn't exist, or that isn't already somebody that's probably more advanced. But yeah, I mean, it's interesting because I kind of would have intuitively thought competition like that, you're going to see vertical axis wind turbines, or you're going to see, some sort of crazy out there wind turbine designs. I don't know, blades made of, cornstarch, or, like just stuff like that. There's like kind of categories of innovation that are pretty normal and not always solving problems that need to be solved, usually not solving problems that need to be solved. So it is interesting that they have managed to kind of, funnel it into, funnel this kind of, innovation competition into really industry applicable types of things. But at the same time, nothing really captured my imagination and made me go, wow, that's such a cool idea. I never thought of that before.
And a lot of software-based technology, right? Virtual reality, simulation, tools for weather, plant tools for planning. It's all software-based, which then gets into the sort of the SaaS play for a lot of venture capitalists, because it can be quick money.
Yeah, I wonder what the competition parameters were. Like, what's the prize? If the prize is $100,000, then it's pretty hard to see how you would install something physically. Do any kind of like real offshore testing. So I think a lot of the times you see too much focus on software solutions because, investors love it because, you can take a clever idea and make a lot of money off it without too much risk. Whereas if you have a brand new wind turbine design, then you need lots of millions of dollars to be able to even know if it does what you think it's going to do. And, a lot of millions more before it would be to the point where you were able to commercialize it. So I suspect it's probably to do with I doubt if Equinor had hundreds of millions on the line for the, for the winners.
No. But I just think where the industry is today, it's the needs are more hardware based than they are software based. My impression. Like, there are real problems happening out in the wind turbine world, and those problems are difficult because they are not software. They are structural issues, electrical issues, and those are hard, right? Because they take cash to create a product to solve them. And it's weird in this sense that the Innovation Hub didn't see that and is not listening to the industry about what the issues are. I think Siemens Gamesa is a good example, right? GE has similar problems. Of if GE or Siemens Gamesa were going to knock on your door and say, we need a solution for X, would any of that be software?
Yeah, I think with software, I mean, it can already take care of it itself. It's not so hard to get funding. I mean, even I think about my friends that are founders, the ones that found funding very easy to come by are the ones with, with software or real kind of like intelligence kind of, where their product is digital, I guess. And the ones where they've got a physical technology that needs to be designed, developed, manufactured, tested, and then, scaled up. Those people, no matter how smart their idea is, they all really, really struggle. But it would be interesting if a company, maybe not Equinor, I mean, it could be Equinor, or any of the major manufacturers, if they ran this sort of thing, then they would be the people where it wouldn't cost them so much. Because you can imagine if you have a new wind turbine design and you're not already manufacturing anything at all, it's a much bigger step for you to be able to test that out compared to someone like Vestas every now and then does like way out there kind of design things. Like a decade or so ago they did this multi-rotor thing, and then I saw a friend of mine recently was actually saying that he was leaving Vestas, and he had been working on a project that had like these ties on to get really long blades. They had tied the blades together at the midpoint of the blade to keep it more more stiff, and probably to help with keeping the natural frequencies under control. Again, I don't think I described that very well, but it's a weird out there kind of thing that you would probably intuitively go, oh, like an interesting idea, I bet it won't work. But that's kind of how every interesting thing is going to start. But you can imagine that someone like Vestas or any of the other manufacturers has a much smaller hurdle to jump to be able to test that, because they're already making other big stuff. And they already have the engineers there that know all the normal things that can go wrong. They've just got to worry about the new things. Whereas if you're designing from scratch and you've got engineers from outside the industry, then it's very easy to go in. It's easier to be creative like that, because sometimes it can be a real like engineers are real party poopers. Someone comes to you with a new idea and an engineer will just tell you 100 reasons why it can't work. And if you don't know those reasons, then you're much more likely to try. So I think it's good for innovation to have people outside the industry, but they're going to experience so many more problems because they don't only have to deal with the new problems associated with, the novelty in their idea. They also have to deal with all the mundane stuff. And so I think it could be really cool to see more competitions like this from the manufacturers, because then that's a way that you can get both the new ideas from the outsiders and then the resources and know-how of the incumbents, and maybe that would be a way that you could see hardware innovation. I think that would be really cool. Anyone needs a judge for their wind energy Shark Tank, then Alan and I are available. And Joel too. We shouldn't leave Joel out just because he's not here.
No. Joel will be really good at that. I think the key about any of these judges is, where do they come from in the industry? Are they a Rosemary Barnes that has been deep inside of a blade manufacturer and who has seen all the ugly things that happen and wish they had a tool to fix some of them? I doubt that's who's on the panel. My guess is that it's more sort of top level people or management people that maybe don't live in the trenches like the engineers do. And I always think, man, engineers would love to have access to this really smart person who knows us one thing, and I want to plug that person in and help us get this problem solved. That doesn't seem to happen in these Shark Tank events. Why, I don't know. But I will say that, you mentioned Vestas earlier. Vestas has invested and did have an innovations group that they were investing in companies they thought had a future, and a lot of them were hardware companies. And I always felt like, oh, yes, that makes sense to me. Like someone internally has said to them, we need a solution for X, and it's not an easy thing. It's not a piece of software. It's a piece of hardware, and it's going to take a year to develop, but we need somebody on it to do it. And they would invest in companies like that. And I haven't seen a lot of that happen, obviously because OEMs are in financial trouble at the minute. But when they get picked back up, Rosemary, don't you think that would be the right thing to do? like to bring in some outside voices. They could be right, they could be wrong, but at least you're not spending a lot of money, but you could, in theory, solve a big problem. In Massachusetts, outside Boston, they have something called the Massachusetts Clean Energy Center. So it's a test center for structural testing of blades. Well, they just received and are starting to use a new structural fatigue test rig that was built and designed and assembled in Denmark by R&D Test Systems. And Rosemary, they're planning on testing blades up to 130 meters long at this facility, sort of right on the water in Boston. And when I saw this, I thought, man, there's no blade manufacturing facilities anywhere near Boston at the moment. Why a test facility in Boston, unless it has something to do with the LM plant up in Canada, and that's right on the water, right? And they could just ship the winter blades right down to the test facility in Boston and test them. I assume that's what's happening. Are there many other facilities that can actually do this work? Is this the only one? I haven't been involved that much on the structural testing of blades, and I know you have seen a lot more than I have. Is this facility unique?
Yeah, it's unique in that it's the biggest currently available. So, I mean, there's some blades getting close to that length that have been made, and they've obviously been tested. Usually what you do when you're testing a really long blade that can't fit in a facility, an existing facility, is that you chop the end of it off and only test the inboard part of it, which to a certain extent, they're actually all blades it's only the inboard part that's tested, which makes sense because that's where, all the big loads are, and that's where they're more likely to fail. And if they fail there, then that's a, catastrophic thing. Whereas on the tip, it's not such a big deal. So yeah, I guess this facility will enable more of the blade to be tested for those long blades, and I guess you can go even longer if you start cutting blades off there as well. It's I don't quite know the reasoning behind the location of it. I guess if it's the only one in the world, then people will go to it, but there's not really anything stopping someone building one somewhere else. But it's just weird. Yeah, it's weird that there wouldn't be one in Europe first, I guess, because, like all of except for GE, all of the big manufacturers that are installing turbines in Europe are all European companies with and I mean, even in, with GE, their blade design is still happening in Denmark primarily. And so it's just a bit strange that you would put your test facility far away from the engineers that are designing it. Because you either want to put it where the factory is, or actually it's kind of easier to put it where the engineers are, because then you can be quite involved in the testing and do a lot more.
Rosemary, can I ask you about that? Because I wonder, when we see some of these blade failures that we've been reading about more recently, how are they structurally testing them if there isn't a facility near them? Are they shipping them all to Massachusetts to be tested? Are there some blades that just don't get tested this way? Like they're testing, the one in Massachusetts has a flapwise and an edgewise motion, right? So they're testing both axes, I guess. Is that common even?
Yeah, you have to do that testing. So everybody does that testing if you want to get it certified and get a blade certificate and have insurance for your turbine and meet your planning planning rules. Then you definitely have to do a flapwise and edgewise test. And so the way that they do it is they take a blade, or at least most of a blade, and they mount it. They at the root where it would normally go onto the hub, they'll put that onto a test rig. And then there are these big like eccentric loads. I'm trying to think of something that is similar to it on a small scale, but it's something that's rotating but off center a bit, and so it kind of gets the thing vibrating or like moving up and down in the natural frequency of the blade. Doing a motion for everyone that's watching on YouTube, but I know that mostly people aren't watching, they're listening. I mean, imagine you've got a drill and then you put your drill bit off center and it's got a mass on it.
Wobble.
Yeah, wobble. That's a Good technical word. And that wobbling is going to excite the blade on the natural frequency, and so it's going to start flapping up and down. So they've got a couple of places where they put these exciters, and it gets the blade moving up and down, and everywhere from the blade root up to where the exciter is, that's being tested. And so they don't put them on the very, very tip of the blade. They put them, a little bit inboard from there. And so it's never the whole blade that's tested. But, they sit there for months doing that. And that's, it's just necessary to do that. But they also rarely fail those tests. And so usually you've already made a lot of blades by the time that your test is completed. And if there was a problem, then it would be a big problem. So they're pretty safe. Usually they're, are on the side of caution and it's really rare to fail one of those tests. You're more likely to fail a static test, which would happen earlier on, where you still mount it in the same way, but then you just put, some ropes and straps on it and pull. And check that it, deflects the way that you expected that it would, and also that it's strong enough. And then every now and then, engineers will just, get a rush of blood to the head and say, you know what, let's break it. And then then they pull it, further than they expect it to go. And you do that just to make sure that your your design code and your analysis methods would tell you at what load you think it should break, and you want to check that you're approximately right, but you never want to design a blade really close to that, because like I said, kind of the whole design process is based around not failing that fatigue test. And especially, it's rare for anyone to fail those tests, because they're pretty conservative and they know a lot after decades of making blades.
Lightning is an act of God, but lightning damage is not. Actually, is very predictable and very preventable. Strike Tape is a lightning protection system upgrade for wind turbines made by WeatherGuard. It dramatically improves the effectiveness of the factory LPS, so you can stop worrying about lightning damage. Visit weatherguardwind.com to learn more, read a case study, and schedule a call today.
Can we dive into this just a little bit? I want to understand more of the structural testing and what we're seeing in the field versus what we're testing in the laboratory. There seems to be a difference, as it's been described to me as an electrical engineer, of secondary vibration modes that weren't necessarily tested in the structural evaluation phase, that they're seeing in the field, which causing some cracking, some disbonds. Is that a function of just not having the right test facility or the right test configuration, or lopping the end off the blade? What's causing some of these things, and why are we not catching them when we're in these demonstration tests?
Yeah, so I don't think that sort of thing is super, super common. So I don't think it's a big oversight, but you do see that sometimes. And the way that they test for that, so and everything's got anything that can vibrate. It has a natural frequency, but it has more than one. It's like with music going up the octaves. You've got harmonics and that sort of thing. And so they'll do simulations, finite element analysis, and also they've got some design codes which are kind of mathematically going through and calculating what the different natural frequencies are. And then you make sure that none of them are going to get excited by anything that you expect the blade to see. So, the tower passing frequency would be one. You wouldn't want to, have the tower passing frequency be something that gets set off resonance in your blade. But then I guess that there are some that are harder to know for sure, and some of the, the aerodynamic loads can set things off, and, you get flutter and that sort of thing. It's in airplane wings too, right?
So we test that. I can describe the flutter test because I've seen it, right? You put a wobbly mass at the end of the wing, and then you turn it on, and it just sits there and vibrates, and to show that it's damped, right? That you don't oscillate to the point of destruction. That seems like a pretty straightforward test to do. I haven't seen anything like that on a wind turbine blade. I assume that's done, or are there flutter tests done?
I haven't seen them physically done. They do more simulations. Yeah, I haven't seen a blade that shook itself apart from flutter either. So I'm not 100% sure of the reasons why it's not as important for wind turbine blades. So
that's very odd, isn't it? I've noticed, just because of the work we do in lightning and looking at aerodynamics, the airflows, because lightning is made of air, we kind of look at blades a little bit differently, but we're trying to see what the airflow is on the suction side of the blades. And a lot of times it looks like it's turbulent, right? On the pressure side, it's always very laminar and smooth and all that. But a lot of times around the tips, it doesn't look like it's flowing in the way that I would expect to see, like on a CFD model. And I always wonder, like, are there things happening out there that are causing some of these weird structurals, these flexing, maybe some twisting that's happening that is exciting in another mode?
Definitely, and the torsional stiffness of a blade, the way that it deflects, like twisting, is way less well modeled than the main kinds of bending modes, like just straight flap wise or straight edge wise. That's pretty accurate between the finite element model, or it's not even a finite element model to start with. It'll be some just some simple calculations using the geometry and materials properties that everyone knows, and it'll run through and design it, and then you use your finite element analysis you use for design features usually, because it's very hard to model a whole wind turbine blade with finite element analysis, because you've got this it's a great complicated design problem, which is why it's what I chose for my PhD on structural design methods for composites, because it's so complicated. You've got the composite materials are the really small scale matters, so you've got the fiber and the resin interaction, and then a little bit bigger than that, you've got sandwich panels where, it matters how the thickness, so the materials are distributed through that thickness. The glue bonds are really hard to model with just your normal sandwich elements. You can't use a 2D model to model a glue feature accurately. And then, they're really big. So, you might be able to model a 1 meter section of a wind turbine with a full 3D model, but, to go up to a 100-meter long blade is really very computationally expensive.
Is that the reason it's not done? Is it because it's computationally expensive? I know in the aerospace world, they've been doing it for a number of years, because obviously there's people traveling in airplanes, but is it really just computationally expensive to do, or is it like an insolvable problem? It needs empirical data to put a solution together.
Yeah, so it's not unsolvable, but it's the empirical data that's a problem as well. And also it's a lot of people, to do the analysis. And all the manufacturers do have teams doing finite element analysis. There's plenty of engineers hired exclusively to do FEAs for any of these manufacturers. So it's not that they're not doing it, but I guess you're kind of targeting where the features are that need this kind of modeling. But the glue joints especially is quite tough, and it really affects the torsional stiffness. So it's hard to model, and it's definitely an area that continues to get a lot of academic research attention paid to it. But like you hinted at, it's also hard to validate. So you can easily measure the deflection of a blade, but measuring the twist is harder. And then with the aerodynamic testing of it, it's very hard to test that in a wind tunnel. Like an aeroplane is very easy to test in a wind tunnel because you can easily scale it. You've got all of the wind is coming in one direction, whereas on a wind turbine blade, because it's rotating and a lot of the speed that the blade sees is actually from the rotation, not from the incoming wind, it makes it very impossible actually to scale it down and get everything to scale at the same rate. So you can't really, some tests you can't do on the scale. You would have to actually, make a big wind turbine, or you can test like a little part. You can test a blade tip and approximate the wind direction and speed that it's going to see, but you're not going to be able to test the whole blade unless you actually get it out on on a turbine. I guess you could always put like little strings all over a real full-sized wind turbine. But even then, I mean, you're not going to know there's wind shear, right? So the wind speed at the hub height is not the same as it is at the tip. And how are you going to know exactly what's going on? So yeah, those are all the reasons why it's a bit hard. And you account for that by having big safety factors at first, early on in wind turbine history, safety factors were a lot higher. And then over time, you start to, as you learn more, you get more confident that there's nothing that you have not thought of, because your turbines aren't failing, then you kind of bring those in. So their safety factors are lower than they used to be in many, maybe most cases. And yeah, you kind of like iteratively get more confident in everything, but you'll always get surprised. And I think that lightning is a really good example of that, where for decades we had lightning protection systems that did a pretty good job. There were failures, but not, an abnormal amount. Everyone was pretty okay with it. And then all of a sudden, recently, so many more failures, things have changed and we're just a lot less sure than we used to be. I mean, would you agree with that kind of summary about lightning?
Yes, I do. And I think it's the same thing on the structural side. So weirdly, the structural side and the lightning side are been tossed a little bit into chaos. Everybody's trying to figure out what's going on. And I more recently have heard of some discussions of particular OEMs looking to add mass or change the weight distribution of some of the blades to dampen out some of these modes that they're seeing, which is really odd because I would assume they would know that going in, like what the modes were for a particular blade, because they have data and like you're saying, because they could probably estimate it off some of the things that they know. It just really gets hard to grasp, like what is going on? Are we just, because we're pushing the boundaries of technology, are we, and like you said, in terms of glues and joints and those kind of things, are those really affecting the overall parameters, the way that a blade moves, flexes, that it's not doing exactly what we thought it was going to do, and some of this is just trial and error.
Yeah, I mean, it's an issue that has popped up every now and then. You're surprised that, you've got some sort of, vibration that you weren't expecting and you have to try and damp it out somehow. I'd say that's like a periodic thing that happens every now and then. Just like, every now and then you get a blade that's noisier than you expected it to be. Noise is another thing where it's really hard to know exactly what it's going to be until you actually, get it really out there. I don't know, maybe I haven't looked at any data or anything. I haven't seen a whole lot of that, but it also might be the sort of issue that is really always caught by the manufacturer, on their test turbine. If it's, if it's a really big problem, then it's going to happen on the very first one. So it might be that it just doesn't get far enough that I would ever get called in to, help, because I get employed by wind farm owners to help them with problems once they're already installed. It's not like manufacturers are calling me in to help them with their engineering. They've got their own engineers.
Well, let me ask you this, because I think it ties in nicely to some aerospace situations that I've seen. Used to make composite airplanes, composite propeller airplanes, and composite jets, right? So you have a composite tube, very similar, and also composite wings. One of the issues that we had in the design of composite airplanes is the noise is horrible. The engine noise is horrible, especially propellers. Inside the cabin, it's really loud. And you would have thought that everybody would figure that out before you have flown the airplane, but they didn't. And so at some of the airplanes, at least one in particular, they added a bunch of lead mass or tuned masses all over the aircraft on the inside to get rid of some of the engine noise and the vibration that way. And I kind of wonder if we're in that same situation, like we got a lot of smart people in a room designing wind turbine blades, no doubt about that. But there's just some things we haven't paid that much attention to, and now they're just starting to peek their heads out, and we got to figure out quick solutions to them. It's a really complicated problem. And I know when you talk to technicians and engineers on the sort of the support side out in the field, what is going on? Why are we having these problems? And no one can really put their finger on it. And weirdly, obviously you don't hear a lot from the OEM, so we have to talk to people like you who were once on the inside to tell us all the magic that happens and why some of these things kind of escape the design engineering group and get out into the field. That it's a really fascinating problem that we need to solve.
Yeah, it is. And I mean, as an engineer, that's the interesting stuff. It's not actually very interesting to just design, the same blade over again. Like, like a standard blade design is going to be basically like a recipe book, right? The manufacturers have done it so many times. They've got the process dialed down that any graduate could run through the steps and come up with a blade that, that was adequate. And that's very boring. So I think to a certain extent, engineers like it when unexpected things happen, because then you've actually got to use your engineering skills, your creativity, your judgment, your experience. And so I don't know. Selfishly, I think it's exciting when things go wrong.
We have to keep following this, Rosemary. And I know over the summer into the fall, we're going to hear more news reports and more stories about some of the blade issues that are happening. And when we get to them, I want you to diagnose them and give us your opinion on them, because it's always interesting to hear what your thoughts are. Our wind farm of the week is Wild Horse Wind Farm in Washington State. Puget Sound Energy operates the Wild Horse Wind Farm in eastern Washington. The site was built in about 2005-2006, with additional turbines being installed in 2009. There are 127 Vestas V80s 1.8 megawatt machines and 22 V80 2.0 megawatt machines, plus a 500 kilowatt solar array that was added. The site was originally developed by Horizon Wind, which was Goldman Sachs and eventually became EDPR. But the thing about this site is that they have a nice visitor center. It's called the Renewable Energy Center and has guided tours. So between April and October, you can go check out all the things that are happening at the Wild Horse Wind Farm in Washington. So Wild Horse is our wind farm of the week. Congratulations. That's going to do it for this week's Uptime Wind Energy Podcast. Thanks for listening. Please give us a 5-star rating on your podcast platform and subscribe in the show notes below to Uptime Tech News, our weekly newsletter. And check out Rosemary's YouTube channel, Engineering with Rosie. And we'll see you here next week on the Uptime Wind Energy Podcast.